All right, welcome to Chapter 7, Part 1, the creation of cloud droplets and rain droplets. So let's get started. After today's online lecture, you should have a better understanding of the process the process of creating water droplets and the process of creating rain droplets. In the process of creating rain droplets, there are 4 processes you need to understand. The idea of equilibrium for a raindrop to survive, the curvature effect that affects the ability for a raindrop to get to equilibrium, the solute effect also affects the ability of the raindrop to come to equilibrium with its surroundings, and the collision and coalescence processes that can happen in rain clouds. So let's talk about these learning goals. So for the formation of a raindrop, the most important thing was liquid water content. So what we already know is when clouds form, they condense on particles called condensation nuclei. So these condensation nuclei are small compared to a cloud droplet. They're only about 0.2 microns. What is a micron? It's 10 to the minus 6 meters. So here's the way to think of a micron. You take a millimeter, you divide that into 10 spaces, take one of those, you divide that into 10 spaces, take one of those, you divide that into 10 spaces. That is a micron. And we're taking that and we're dividing into 10 spaces and taking 2 of those. That's 0.2 microns, incredibly small. Now, a typical cloud droplet is about 100 times larger, or 20 microns. And then a rain droplet is about 100 times larger than that, about 200 microns, or about 2 millimeters in diameter. All right, there's several things that affect the cloud droplet's ability to survive. And what we want to do is talk about equilibrium for water molecules leaving its surface must be equal to the number of water molecules entering a surface. We've talked about that before. So when that happens, we have saturation. And if this isn't happening, then the droplet will evaporate. So we call this point at which we have saturation vapor pressure. We've talked about that before. And in this case, since we're looking at the process of equilibrium of a raindrop between its surroundings, we call this equilibrium vapor pressure. And that's basically the same thing as saturation vapor pressure, except we're talking about the ability for a cloud droplet to survive. It needs to be in equilibrium with its surroundings. If it doesn't, then the cloud droplet will evaporate. All right, so these ideas hold for flat surfaces, okay? And unfortunately, our droplets have surfaces are curved, and so this is what we're going to call the curvature effect. Now, the curvature effect depends on the curvature of our surface. The more curvature, the larger the effect. So small objects have a larger curvature effect than larger objects. So cloud droplets have a larger curvature effect than a rain droplet. All right, so what is the curvature effect? Well, you just got to have more water vapor surrounding it than you would for a flat surface. See, here, I'll show you a picture for what. So here's our flat surface right here, and it's in equilibrium when we only have 4 water vapor molecules above it, right? But if we have this curved surface of a cloud droplet, look how many more water molecules have to be there in order for the cloud droplet to be in equilibrium. Looks like almost 10 times more, or much larger than the flat surface. Now, if it doesn't have this, our rain droplet will evaporate. So now we're going to talk about the solute effect. Basically, if water dissolves a material, say like sodium chloride or salt, you get sodium ions and chlorine ions in the water. Now, when this happens, some of these ions go to the outer surface of the water molecule, so that means there's less chance for a water molecule to be on the surface, and so less water molecules will leave the surface. So this causes pure water to evaporate faster than something that has a solute in it or something dissolved in it. The most common things that dissolve are what we call hygroscopic nuclei. More common ones in the atmosphere are salt, okay? So we can get salty water raindrops over the ocean. And another common one is acid rain. Some of the aerosols and particulates released by pollution can dissolve in water and cause the water to raise in acidity. And this gives us the so-called acid rain. Our last process is the collision and coalitions process. So when water droplets form, they reach what we call terminal velocity. Every object has a maximum. What is terminal velocity? Basically, is every object has the ability to fall, and the fastest velocity it can get is what we call terminal velocity. This terminal velocity depends on the size. So larger droplets fall faster than smaller ones. So you see over here, this larger droplet will be falling faster, and it will catch up and pass some of these cloud droplets here. Okay. As it does that, it gathers them up in front of it and will absorb them. By overtaking them, you have collisions with smaller ones. And so this process is called coalescence. All right. So now as the water droplet falls, it sweeps out all the cloud droplets in its wake, and this causes a pressure difference. There's more water molecules here than here, so these water molecules want to move in here. Same on this side. And then as they get pulled in, they can also get captured by the water molecule, and we call this wake capture. And this can also add to the growth of the raindrop. And these processes are called the collision and coalescence process. Now, how can these processes be enhanced? One of the main reasons is this happens in relatively warm clouds. The tops of the clouds are usually warmer than minus 15 degrees Celsius, and in clouds, minus 15 degrees Celsius is considered warm. Most important factors in the production of rain droplets is, again, the liquid water content of the cloud. If there's not enough liquid water condensing, you're not going to get that many rain droplets to form. Now, this coalescence appears to be enhanced if the droplets have opposite electric charge. And what can happen is one property of matter is called charge. And then you have two types of charge. You have positive charge and negative charge. And if they're both opposite, these charges attract. And this gives, if a water droplet has a charge on it, it will attract the opposite charge. And so more chance of drawing more cloud droplets towards it, and then the raindrop grows. All right. So if we have a thicker cloud, there's more time for the water droplet to fall, and a chance for more collisions, and then the rain droplet can get bigger. Now the other effect is this updraft idea, and here's an updraft, okay? So if the cloud droplet forms down here, the updraft can carry it up higher and have a chance for more collisions with cloud droplets, and it should grow. Once it gets large enough, the updraft cannot lift it up anymore, and it will fall back down again, colliding in coalescence with other cloud droplets getting bigger and bigger. And so this is another strong effect, or another effect that can affect the ability of a cloud to create rain droplets. And the other effect that can enhance it is, again, electrically charged rain droplets can attract oppositely electrically charged raindrops. So a raindrop could be positive charge, a cloud droplet could be negative charge, and they would attract each other and form larger raindrops or larger droplets also. So I hope after this you have a better understanding of the process of creating water droplets, the process for creating rain droplets, the idea that equilibrium has to be there in order for the cloud droplet or rain droplet to survive. The curvature effects can affect equilibrium, make it harder to reach equilibrium if the curvature is small, and the solute effect can help a rain droplet get to equilibrium and survive the falling. And the collisions and coalescence of other water droplets in the atmosphere can also help the rain droplet form. So be sure to watch part 2 of this online lecture so you can understand the rest about what causes precipitation. So I'll see you.